Okay, so we're going to look at how to answer titration questions using first principles. So the hint to how to know as to when to use first principles is when in the maths questions they ask you for the average number of moles of HCl or whatever the substance is used up in a specific amount of solution. So for example, the average moles of HCl used up in a titration, then up here it says the average amount is 21.5 centimeters cubed used up in each titration. So that's how to spot them, rather than using your MA by VA over NA equals MB over by VB over NB formula. So that's how to spot when to use first principles in answering one of these titration questions. So if you want to just pause, read over the question, and then we'll get started. Also, whenever they're asking you for the average number of moles of whatever solution it is, that solution is usually the standard solution. So to see how it says previously standardized HCl. So that's another way to spot it. So the first question, the average number of moles of HCl in a specific amount of a solution, and that solution is up here the standardized solution. So that's how to spot when to use it. Now we're going to answer D first of all, because that is our calculation part of the question. However, there are some parts up in question B that we will need to use to answer all of question D. Okay, I'm just going to write out everything I know about the hydrochloric acid and everything I know about the sodium carbonate. So we have 21.5 centimeters cubed of the solution used up in each titration. 0.12 moles per litre is the molarity. And then the number associated with the acid here is 2 from our chemical formula. Over to the base then. The amount of the base used in each titration is 25 centimeters cubed. The molarity of the base we don't know. And the number associated with the base in the chemical equation is an imaginary 1 there, is 1. So you might be thinking, why don't I just straight away use this MA by VA over NA formula with the association base values? And it's because if we do that, we would get an answer for the molarity of the base to be something moles per litre. Now you can work your way down after you get, let's say, a number for the amount of moles per litre. You can figure out, okay, well, how many moles are in the 25 centimeters cubed of the solution. And that would be answering this section here. But if we're using first principles, we're just going to skip that part and work away with what we have. So the average number of moles of HCl used up in a titration. So you're going to be using this formula, if you remember it. The number of moles equals volume times the molarity over 1,000. Now, if you didn't remember that formula, I'm going to show you, bring you through the thought process of how to actually answer these questions. And it's probably better to understand the thought process step by step, because sometimes you're not given the volume. You might be given grams dissolved in solution or literally just the molarity. Okay, so knowing the thought process of how to work out how many moles are in a specific amount of solution is better than knowing just this formula. Okay, but just know that you can use that if you have the volume. So I'm going to go through how to answer it using the formula, and then I'm going to go through the thought process. So the number of moles is what we're trying to find out. We have 21.5 centimeters cubed of the volume of the HCl. The molarity is 0.12, and then divide by that by 1,000, and we should work out how many moles are in that specific amount of HCl. And that should work out to be 0.00258 moles of HCl in the 21.5 centimeters cubed. Okay, now I'm going to bring you through, if I just did not remember that formula at all, how we can answer it. So I know the molarity of the HCl is 0.12 moles per litre. Now 1 litre is 1,000 centimeters cubed. So I know that there's 0.12 moles of HCl in 1,000 centimeters cubed. So in 1 centimeter cubed, I'd have to divide this line here by 1,000 to get what it would be in 1 centimeters cubed. So I'm going to take that 0.12, divide it by 1,000 to see how many moles are in 1 centimeters cubed only. Okay, now I don't want it in 1 centimeters cubed. I want 21.5 centimeters cubed. So I'm going to take that number for how many moles were in only in 1 centimeter cubed and multiply it by 21.5 to see how many would be in that amount of solution. And when I do that, I get this answer. Okay, so that's the first one done. So 0. In the 21.5 centimeter titer, we had 0.00258 moles of HCl. Second question is the average number of moles of the sodium carbonate neutralized in each titration. So again, it's asking for the number of moles basically in the 25 centimeters cubed of the washing soda solution that was neutralized each time. So I know up here that in the HCl, I have 0.00258 moles of that HCl. Now the HCl reacts with the sodium carbonate in a 2:1 ratio. So if I don't have 2 moles of it reacting with 1 mole of sodium carbonate, I have 0.00258 moles reacting with a certain amount of moles of the sodium carbonate. So it takes twice as much HCl in terms of moles as the sodium carbonate. So I'm going to have to just divide this number by 2 to figure out how many moles of the sodium carbonate I have. So when you take 0.00258 and divide it by 2, you'll work out that the number of moles of sodium carbonate is 0.00129 sodium carbonate used up in each titration. So that's the first 2 done. Then number 3. The number of moles of sodium carbonate in 250 centimeters cubed of the solution. Well, we just worked out that there was this amount of moles in 25 centimeters cubed, basically, and we're seeing that in our question, that each time we had a titration, it was using 25 centimeters cubed of the solution. So how many times is 25 go into 250 10 times. So if I want to work out how many moles is in 250 centimeters cubed, I just take the amount of moles in 25 centimeters cubed and multiply it by 10, and I would get 0.0129 moles of the sodium carbonate in 250 centimeters cubed, which is actually the amount I made up to in the first place. See up here, we had a certain amount of grams of the crystals and we brought it up to 250 centimeters cubed. Okay, that's the third one answered. Then part 4, the mass of sodium carbonate in 250 centimeters cubed of the washing soda. So I have the number of moles. I should be able to easily convert to mass now. But just to bring it back to the first principles, these first two are basically the part where you do the first principles. You're using all of your skills used in the stoichiometry chapters when you're working out the number of moles, and then using that to work out the ratio 2 to 1, which is what we've done. So we haven't used the MA by VA over NA formula at all when we're answering this titration question. Okay, back to now converting this amount of moles into grams. So we take the number of moles equals the mass over the relative molecular mass, 0.0129 moles of the sodium carbonate in the 250 centimeters cubed. We don't know the mass. The relative molecular mass is 2 times 23 plus 12 for carbon and 3 times 16 for the oxygen. And all of that added together works out to be 106 on the bottom line for the relative molecular mass. Bring that across and it turns into a multiply. So the mass of sodium carbonate in the 250 centimeters cubed is 1.367 grams. And that's the fourth one done. Now the fifth one, the mass of water of crystallization, and hence the number of moles in the 3.46 grams of the crystals that we used in the very first part to actually dilute the solution. So I'm going to wipe all of this out. And I'm just going to keep that number there. So now we need to bring in that 3.46 grams that was in the question. So I've worked out how much of the pure sodium carbonate is in the solution, because that's the active ingredient. That's the part that's actually going to react when we're doing this titration. The water does not react. So this is the total amount that was weighed out. And if I take away the amount of sodium carbonate that I've figured out is in that sample, I'll work out how much water, this part, is in water crystallization is also in the crystals. So taking those two figures away from each other, I'm going to end up as in the water of crystallization in the sample is 2.093 grams. Okay, and that relates to this X times H2O section. So 2.093 grams is how much water of crystallization was in that original sample that was diluted into the water and made up to 250 centimeters cubed. Now you want to convert that to the number of moles of water. So again, that's just a simple number of moles equals mass over the relative molecular mass. We have 2.093 grams of water. The relative molecular mass of water then is 2 times the 1 plus 16. Work that out and we should get 0.1163 moles of water. That's that question answered. So we're on to the last one now. The ratio of moles of water of crystallization to the moles of sodium carbonate in the crystals. So previously we worked out the number of moles of sodium carbonate in the 250 centimeters cubed, and we worked that out to be 0.0129 moles of the sodium carbonate. Okay, so now we want to see the ratio. It literally says it in English. You're just going to convert that English sentence into a ratio. So the number of moles of water compared to the number of moles of the sodium carbonate. Okay, let's fix that there. So then just put in your figures. Okay, so they obviously combine together in the sample in that ratio. So I just want to bring it down to the simplest ratio. To do that, I should divide each number by the smallest one. So the smallest number there between the two is 0.0129. So divide 0.1163 by 0.0129 and 0.0129 by 0.0129. And I'll work out this side to be rounding up to be about 9 and this side to be 1. So that means, hence the value of x to the nearest whole number, that the sodium carbonate crystal bonds with 9 water molecules around it. This Na2CO3.X-H2O, that's just a ratio. That dot means that one molecule of sodium carbonate reacts with how many molecules of water. Now remember, water is this side and the sodium carbonate is this side from what I was doing up here. So 1 is to 9. So I can rewrite this now as Na2CO3 reacts with 9 moles of water. And that's that question done. Now, if we look at another example, try and see from what I've already said if we're going to use first principles with this question or not. So I have a little read through. Okay, so you should have seen that our primary standard is the ammonium iron sulfate. And the first question is the number of moles of iron in a specific amount of the standard solution. So that again is your hint to use first principles. So let's work our way through it. The number of moles of iron in a 25 centimeter cube solution. So let's write down everything we know about the iron solution. So 25 centimeters cubed. We have the mass of 8.82 grams of the crystals. And that's all we seem to know about it. So it's not the volume this time we're given mass. So I'm going to take the mass and convert it to moles. Whenever we're dealing with these type of questions, moles is always like the home base that we go to. So volume, mass, whatever, convert it into moles. Okay, so because that's how chemists count. So we're going to take that 8.82 grams and then divide it by the relative molecular mass of this substance here, our hydrated ammonium iron 2 sulfate. So once you take all of the relative atomic masses of all of those numbers, making sure to multiply it in properly. So like nitrogen is actually 2 times 14, 2 times the 4. So that'll be 2 times 14 plus 2 times 4 is 8, 8 times 1, plus the 32 for sulfur, plus the 4 times 16 for the oxygen, plus iron, 56, plus sulfur again, 32, 4 times 16 for the 4 oxygens, plus 6 times 2 for the hydrogen is 12 hydrogens, 6 times the 1 oxygen. Add up all of that and you should get 392 for your answer there. So the mass over the relative molecular mass is going to give you the number of moles or the molarity, let's say. So we work that out and we're going to get 0.0225 moles. Now, is it in a litre? Or how much did we make that up to? We made it up to 250 centimeters cubed. So that is the number of moles in 250 centimeters cubed. Okay, not in a litre. So writing down this extra sentence just to make sure that you're staying on track rather than just writing down this much information on that side is much better, and it's going to keep you on track when you're doing out the calculations. Okay. And that's the amount of iron in the solution. That's the iron part, is the reactive ingredient in it. Okay. So the question is asking in a 25 centimeter cubed portion. So let's go again with the top process. That's the amount of moles in 250 centimeters cubed. If you're able to do it, you can go straight to 25 centimeters cubed. But if you can't, we can bring it down to in 1 centimeter cubed. We have how many moles? So you're going to take 0.0225 and divide it by 250, because 250 divided by 250 is going to get you the 1 centimeter cubed. So we're going to have to divide this number by 250 as well. Okay, so when I work that out, that's going to give me 0.00009 moles of iron in 1 centimeter cubed. So in 25 centimeters cubed, I'm going to take that number and multiply it by 25 to get how many moles is going to be in 25 centimeters cubed. Okay, so that's number 1 done. Number 2, the number of moles of potassium permanganate required to oxidize this quantity of the iron. So remember stoichiometry. We're going to take the ratio of the reactants and take a look at that. So MnO4 minus reacts with iron into 1:5 ratio. So that means if I have 1 mole of the manganate solution, 5 moles of the iron solution are going to react with that. Now I don't have 5 moles in my number of moles of the titration. I have 0.0025 moles. So how do I get back to the 1? I need to divide that number by 5. So on the side, 0.0025 divided by 5 is going to get you the number of moles of potassium permanganate needed to titrate it against the amount of iron, which I'm going to get 0. Sorry, that should be a question mark there, or an X. 0.00045 moles of the potassium permanganate is going to react with the 0.025 moles of the iron solution. Okay, next question. So there was what we've learned from the previous question. 0.0045 moles of potassium permanganate is used up in each titration. The next question is the molarity of the potassium permanganate solution. So that wants it in moles per litre. So what links with that amount of moles? What volume links with it? Each titration. So try and find that there. So on average, 20.45 centimeters cubed of that potassium manganate solution. So we worked out that 0.00045 moles is in 20.45 centimeters cubed of the solution. So let's bring it down into what's in 1 centimeter cubed. So I'm just going to have to divide each number by the 20.45. Remember, all of that converts to 1 centimeter cubed. Working that out on the calculator then. We're going to get 0.000022 moles. Bringing it back up to how much is in a litre. Remember, 1 litre is 1,000 centimeters cubed. So we're going to multiply this whole line, top line, by 1,000. So 0.00 by 1,000. So in 1,000 centimeters cubed, we have 0.022 moles. So remember, 1,000 centimeters cubed is a litre. So we have 0.022 moles per litre, which is your molarity of the potassium permanganate. Okay, and that's how to do first principles. So it's basically just stoichiometry brought in to our titration questions. And we know, remember the hint, it's asking you for the number of moles in a specific amount of solution, and that solution is usually your standard solution in the titration.